Okay, we're going to talk about operations with functions. There's going to be 5 operations. Well, 3 and 2 sort of operations, but there's going to be 5 items we're going to look at. So there's going to be addition, multiplication, not to be confused with composition. So there's going to be addition, multiplication, composition. Many of us have not seen composition too extensively or at all, so we have to make sure we understand this is sort of new for many of us. And then we have the subtraction, the division, and then in the next video we're going to do the inverse, which is sort of undoing the function itself. So addition, multiplication, not to be confused with composition. The symbol for composition is a small circle. It is not a dot. It is bigger than a dot. It is big enough so we can see it is a circle, yet it is not so big that it can be confused with a 0 or with an O. So this is a new symbol, and it is the composition, the symbol for composition of functions. Composition of functions. So that is the symbol we're going to be using. And we also want to be able to undo some of those, I'm going to call them operations for now, but in my opinion, the only operations are those 3. Those 2 are not operations because they are not associative. So those 3 are the operations, and those are the undoing of those operations. Anyway, let's start with addition. Oh, there's one other thing. We have to pay close attention to domains. Domains are going to be very, very important. So domains are going to be crucial. We have to pay attention to the domains. And let's get started with some examples. So let's say we're given 2 functions, f of x equals, let's start with 2 linear equations, say 2x plus 3, and g of x, 4x plus 5. All right, so we're going to define a new function, f plus g of x. So again, this is a new function made up by those 2 functions. And the way we obtain this function is by adding the outputs. So that's quite straightforward. So 2 and 4, since the outputs are made up by those polynomials, the addition of the function is going to be made up by the addition of the polynomials as well. So we're going to end up with 6x plus 8. And that's it. That's it. Yes. Now, if we ask to break this up into the addition of 2 functions, so as an example 2, we can ask to break up. So I'm going to come up with a new name. Let's label it h. h of x equals 6x plus 8 into 2 functions, into 2 functions via addition. Okay, then we have several choices. You know, we can go back and now see, this is kind of weird because if you already know where this came from in the previous example, you may say, oh, I can do 2x plus 3 and 4x plus 5. But somebody else who has not seen this previous example would say, wait a minute, why not rather 6x and 8? So we could think, let me add here into two functions, f and g. So those are two separate examples. I'm using the same output, but those are two different examples. So let's pretend you didn't have this problem. If you had this one, then there's many solutions. Be aware that there could be many solutions. Somebody could say, wait a minute, I could have f of x equals 6x and g of x equals 8. And when we add them together, we end up with this function. So that is a good answer. Somebody else could say, could I do f of x equals x, and then g of x equals 5x plus 8? Sure, that is a good answer. In this case, I don't think one is necessarily above the other. This one is a little nicer because we're actually coming up with two different kinds of functions. This is a linear function, while this is a constant function. So this one is a little bit better than this one. Here we're not really coming up with something new. They're both linear. So this one is slightly better, but in this particular case, I don't think this is wrong. Now, the one thing we want to avoid, so we're still in this example too, avoid trivial solutions. So what are trivial solutions? Solutions that don't add any additional information about the original function. So here we're breaking up into simpler functions. Even though this is very similar to the original function, it is a little bit simpler because we're using a smaller number. But somebody could come up with a very, very interesting answer. F of x equals 0 and g of x equals 6x plus 8. Okay, so if we add those together, yes, we will end up with the original function that we want to break up into two functions by addition. But we're going to label this as trivial because we're not really decomposing the function into simpler parts. So it's a trivial decomposition. So we're not going to admit this. In fact, oftentimes I'm going to add, when I ask this kind of a question, break up into two non-trivial functions. So the non-trivial will be there somehow, somewhere. Maybe I can add non-trivially. Yeah. So this will be excluded as a solution. We don't want to have a solution where we're not really doing much. Also, we want to avoid overly complicated solutions, unnecessarily complicated solutions. Avoid unnecessarily complicated decompositions. I'm probably not going to add this to the question to avoid unnecessarily complicated solutions, but it is going to be understood. So what is an unnecessarily complicated solution? Somebody could say, well, why don't we do f of x equals, I don't know, 100x plus 1000, and then g of x, so we need a 6x, so that means we have to put negative 94x, and we need 8, so negative 992. So does the addition of those two make up this original problem? Sure, 100 minus 94 is 6x. 1000 plus negative 992 is 8. But this is overly complicated. This is not what we mean when we say we want to decompose, break up into usually we mean simpler parts. I would say this is the best one because that actually breaks it up into something that is simpler, not something that is, this is even more complicated. Somebody could say, well, can I do x squared and negative x squared? I mean, you can add anything you want. Yeah, but this is not valid. It is technically correct, but it is not acceptable. That's probably a better word to use. Not acceptable. Yeah, we don't accept this kind of thing because we're making something complicated, and typically when we want to break things up, we don't want to break them up into something that is more complicated. Usually we want to go the other way. I can see instances where we want to do that, but most of the time we want to go the other way. We want to go into something simpler. But there are instances when we do that on purpose, and that's okay. So subtraction is very much the same. Example 3. So let's go the other way. Say f of x equals 2x plus 3, g of x, so this is given, equals 4x plus 5. So what is f minus g? This is going to be a new function made up by those two functions of x. And what we do is subtract corresponding outputs. Since the outputs come from the polynomials, if we subtract the polynomials in the same order, we're going to end up with a new polynomial that generates all the outputs. So 2 minus 4 is negative 2, x, 3 minus 5 is negative 2 without an x, and that is it. Something I did not spoke about was the domain, and we should talk about the domain here in this example, example 1, back to example 1. The domain of this is all real numbers. The domain of this is all real numbers, and remember that is implicit domain. We spoke about that in the previous video. So the combination of the two will have a function that is still all the real numbers. But you gotta watch out, because if one has a particular domain, then that's gonna restrict the domain of the combination of the functions. Yeah. All right. We could decompose in using subtraction. Typically, we don't do that, but we could do that. So let's go back the other way, I suppose. Let's do an example of that. Let's say somebody gives you h of x, given this, equals negative 2x minus 2. And so let's just say given. Then find f and g so that f minus g equals h. So here we have many ways to go about it. Somebody could say, well, let's do 4. Yeah, that could be one way to go about it. F of x could be 4x plus 4. G of x could be 6x plus 6. So that when we subtract, we end up with this. Yeah. So, but somebody could say, what about f of x equals 5x plus 5? And somebody else, well, and then for g, 7x plus 7. Well, that works. That works. Somebody could say, well, how about, and this is a little more complicated, f of x equals negative 2x and g of x equals 2. That works. And actually, I would prefer something like this, because then we're breaking up the original function into two pieces that are different. But those two are good also. Yeah, we typically want to not have a trivial solution. zero. When zero is involved with addition, then we have a trivial solution. So we want to avoid those. And again, overly complicated should be avoided unless there's a context that in which we are going to benefit from having a complicated solution. Multiplication is very much the same. So example 5. In example 3, I did not speak of the domains because the domains are all the real numbers. Where's example 3? There it is. So here, real numbers, the combination of the two are still the real numbers. There's no problem with the domain. So the domain is still the set of all real numbers. There's going to be some trick questions. I'm very likely to ask you where the domain is not going to be all the real numbers, but I'm going to reserve those examples, or I'm going to emphasize the domain as we get into those examples. Okay, so 5, let's speak about a multiplication. So again, 2x plus 3, and then 4x plus 5. So if we want to multiply f and g, or we can come up with a new function. Sometimes we put a dot, sometimes nothing, and that implies multiplication, and that is a new function that is made up by multiplying the outputs of the corresponding inputs under those functions. Since the outputs are made up by polynomials, we can just multiply the polynomials and end up with a polynomial that it corresponds to the output of this product function. So this is 2x plus 3, 4x plus 5, and then we can FOIL this to end up with 8x squared. 2 and 5 is 10. Outer terms, inner terms is 12x, 15, and finally we end up with x squared plus 22x plus 15. So that is the product. The domain is all the real numbers because those were the domains of those two, and there was no issue, problem, complication with those two. Okay. Yeah. Breaking up into factors, we would have to, okay. So if we were to break this up into factors, into two functions, the most logical way to do this is to end up with the corresponding linear factors where this came from. So again, coming up with factors of this, so let's say you're given the reverse problem, example 6. Okay, so given h of x equal to 8x squared plus 22x plus 15, if we were asked to find f and g, whoops, not h, g, so that fg equals h, then the most logical thing to do is to factor this out, and then one of them is going to be f, the other one is going to be g. Since multiplication of polynomials is commutative, it doesn't matter which one is f and which one is g. We don't have to have that as f and that as g. It could be the other way around. So one possible solution could be f of x being 2x plus 3, g of x equals 4x plus 5. Good. If another student comes along and says f of x is 4x plus 5 and g of x is 2x plus 3, I have to admit it as good. Of course, either one of those two will be completely correct. The one thing that will not be accepted as far as splitting up into f and g, and even though I did not specify here non-trivial, it is pretty understood that we shouldn't do this, even though technically it is correct. Somebody could say, hey, I can just make f 1 and g 8x squared plus 22x plus 15. This is technically correct, technically accurate rather, but trivial. So not allowed. As an answer for breaking up a polynomial function into two factors. That is not, we don't want to do that. Again, it is trivial. You can always use one. We did not really break this up into simpler pieces. Uh, those linear functions are simpler, each one of them, and together they make a more complicated function. But this is not really breaking up into two simpler functions. We still have the same complicated function that we started with. So this is not adding new information to our problem. Now, when we say a product, we cannot exclude the one because otherwise we have to make too many exceptions. And you may be thinking, well, are you making an exception here? Yes, but it's better to do it on this end than on the other end. Um, yeah. So we don't want to do that. And then unnecessarily complicated examples of this could be, so I'm still under example 6. Say you want to decompose this into two functions. Somebody could say, well, I could choose f of x to be 1/4 and g of x to be 2x squared. Oh, no, that wouldn't work. It would be 32x squared plus 88x plus 60. So why? Because if we multiply those two, we end up with the original problem. Can we do that? Yes, this is accurate. So accurate, but unnecessarily, I think I'm misspelling necessarily, but I don't want to check it right now, necessarily. So please double check the spelling. Unnecessarily, yeah, check spelling. Accurate, but unnecessarily complicated. And those people who say, well, this is not a spelling class, so we shouldn't care. No, I disagree. We should care. The fact that we are in a math class doesn't mean we shouldn't care about our spelling, grammar, writing, etc. Anyway, going back to this, the original problem has simpler numbers, 8, 22, 15. These are more complicated problems, rather numbers, 32, 88, 60. And then 1/4 is a fraction. So we're really making this more complicated than it has to be. Why would we want to do that? We are not gaining anything. The point of splitting things into parts is so that each one of the parts is simpler to deal with. That's typically what we want to do. Now, having said that, yes, there are instances where we may want to do things more complicated because then that will fit the rest of the problem better. Yes. But if we don't have a bigger problem that we're working on where maybe the 1/4 will help us combine with another fraction that already has a fourth, that's what I'm trying to say. So let's say we were adding fractions and one fraction already has a fourth in it as a denominator, a 4 as a denominator, then yes, this can benefit, or doing this will benefit combining the 1/4 that we may have somewhere else. But by itself, it doesn't seem to benefit us at all. So we don't do it. We consider this unnecessarily more complicated, and consequently, we don't allow it. So we do not allow. Again, I want to emphasize, but that varies depending on the context. See, in math, believe it or not, we have to use good judgment. I think math helps us develop good judgment because a lot of people say, well, in math, there's always a right and a wrong. But yeah, but then there is the correct or there is the appropriate So is it bad to use 1/4? Well, if there's no benefit to it, then yeah, it is not, then we're making things more complicated. But if there was a benefit to it, and sorry to repeat myself, then it would be perfectly appropriate to use 1/4. So so this is one of those cases where is there a right or a wrong answer? Well, it depends on the bigger picture, and that helps us develop good judgment. Um, Division. Oh, there's one thing about division that I want to emphasize. I was almost going to skip division, but we shouldn't. Yeah. So 7. If you have given f of x equals 2x plus 3, g of x equals 4x plus 5, then um, division f over g of x is a new function. And you know the drill, you take this polynomial, you divide by that polynomial, 2x plus 3 over 4x plus 5. And that gives us the formula. But there is one more thing. There's an implicit domain that shows up that is different than the domains that we started with. This domain of this function is all real numbers. The domain of this function is all real numbers. But when we divide, we have to assure ourselves that the denominator cannot be 0. There is one number for x that will cause this denominator to be 0. And we want to avoid that. That denominator, or that x value, will be -5/4. So we have to avoid comma, avoid x equals -5/4, because if we were to plug that in here in the denominator, we will have 4 times -5/4, which is -5. The 4's cancel, so we end up with -5. But then we add 5, and that's going to give us 0. And we may never, ever, ever divide by 0. So we have to avoid this. There's a shorthand for this, and that would be x cannot be -5/4. Yeah. So that is a shorthand. The proper way to write the domain using interval notation would be from -∞ to -5/4, close parenthesis, union -5/4, all the way to infinity. So with division, we have to be extra careful. Actually, yeah, because if the domains of the other two are all real numbers, things are not going to be changed too much. But if we divide, then we have to pay close attention to the denominator, which cannot be 0. All right, so there's not too much new about addition, subtraction, multiplication, and division. Composition is quite a different animal altogether. Composition, and by composition in algebra, we mean composition of functions. Yeah. So what composition of functions does is that it takes the output of one function and puts it as the input of the other function. Very, very interesting. It takes the output of one function and puts it into the input of another function. So, example 8. Given f of x as 2x plus 3, g of x as 4x plus 5, okay, we want to find a f composed with g of x. And then there's going to be a b, but I want to write b after we finish a. So f composed with g, and then there's going to be a c and a d. All right. So by definition, f composed with g is f of g of x. So the input of f is going to be g itself. So f says take, and remember what the formula is about. The formula in this case tells us take whatever the input is, multiply it by 2, and add 3. So in this case, the input is going to be g. So this is going to be 2g of x, and then add 3. In turn, g is 4x plus 5. So we're going to multiply the 2 with the entire quantity of 4x plus 5. Then add 3. That's going to give us 8x plus 10. Still add the 3. And finally, we end up with 8x plus 13. Okay. B, let's find g composed with f, which is g of f of x. Now, g says whatever the input is, multiply it by 4. After multiplying by 4, then add 5. So we're going to multiply by 4 the current input, which is f of x, and then add 5. In turn, f is 2x plus 3. So this is 4 times quantity, 2x plus 3, and then add 5. Well, that is 8x plus 12. Still add 5. And that gives us 8x plus 17. One thing to notice, this is the answer to g composed with f. This is the answer of f composed with g. One thing to notice is that they're not the same. They're similar. They both have 8x with it, but this one has 13, while this one has 17. Very, very different. They're not the same at all. Even though they're similar, in mathematics, things either are equal or not equal. They're not equal. They're not the same. Which leads to an important note. F of g, rather, f composed with g is in general not equal to g composed with f. And we just gave an example where they're not commutative. Now, when we say that an operation is commutative, that means that it will apply to every single number or every single object. So for instance, addition is commutative. You know, addition of functions, f plus g, is definitely always, always, always equal to g plus f. That's always true. But commutative of composition is not always true, and consequently, we say that they're not equal. This is kind of weird because there's going to be examples where they are going to be equal. But there are other examples where they're not equal. So when they're not equal, every single time we say that they're not equal. C. So we're still under the umbrella of example 8, where this is f and this is g. Nothing stops us from using f or composing f with itself. You know, just like nothing stops us from adding 3 plus 3. We don't have to add 3 plus something other than 3. We can add 3 plus 3. Well, likewise here, we can compose f with f. So f says, oh, well, let's write what the definition is. F of x. Now, f says whatever the input is, multiply it by 2. After the multiplication has been performed, then add 3. So multiply the input, which is f of x, by 2, and then add 3. But F itself is about multiplying twice the input of F and adding 3. Okay, so 2x plus 3 times 2. And then we do the algebra. I was thinking, F can be composed with itself, and that made me think of a cartoon I saw many years ago. I think it was about the Pink Panther, in which a vacuum machine was sucking up itself, and eventually, the hose was sucking the body of the same vacuum machine and eventually disappeared. That made me think of this like a function. I mean, this is not going to disappear, of course, and perhaps that is a silly analogy, but it made me think of it because I thought, okay, so there is like a vacuum machine, sucking up to itself. It's doing what it does to itself. I don't know, that maybe that is a weird analogy, but it made me think of it. So anyway, here we end up with 4x, and if you don't mind, I'm going to do 2 steps at once. That is dangerous. Watch out. But I like to be wild once in a while. And so I'm going to multiply by the 2, and then I'm going to add 3. I know that's 2 steps in one. And sometimes I like to live on the edge of things. So so 2 times 3 is going to be 6, plus 3 is 9 there. So the answer is 4x plus 9. Yeah. Yeah, when you do that, you got to be careful because if we make a mistake along the way, it is going to be more difficult to track where the mistake originates. D, and you know what D will be, G composed with G of X. And G calls for 4 times whatever the input is. See, I'm skipping a step because I didn't say G of G. I'm going directly to what it is. 4G of X plus 5. G in itself is 4 times 4x plus 5 plus 5. See, this is the part that makes me think of the vacuum machine sucking up itself. And then that is 16x. And then I'm going to skip a step, and that is going to be 25 because 4 times 5 is 20 plus the 5, 25. Yeah. Yeah. So that is that. And nothing stops us from doing something 3 times. So the E, example E, this is going to be a longer example. Let's say we do F composed with G composed with F again. So now we are combining 3. Just like with addition, we could add 3 functions. With multiplication, we could multiply 3 functions. We didn't do examples of those, but it is easily extended. With composition, we can compose 3. And notice that I didn't put inside parentheses. By that, what I mean is, should we do F composed with G first, and then whatever that is, compose it with F? Or should we do G composed with F, and whatever that is, do F composed with that? As long as we keep the order, very, very important, as long as we keep the order the same, correct, from left to right, it doesn't matter whether we do the last 2 first and then do F with whatever the answer is of that, or if we do the first 2 first and then whatever the answer is of that combined with F. So let's go ahead and do this. Now we did F composed with G in part C. Oh, no, in part A. That was our very first part of this example 8. F composed with G is 8x plus 13. So we're going to do 8x plus 13, but so the 8x plus 13 comes from this. Maybe I should make a quick note of this. This is 8x plus 13 if the input is x. If input is x. That's from part A of this example. But now the input is going to be f. So we're going to do 8f plus 13. Now this is from a, so we're going to piggyback on part A. If we did not have part A already done for us, then we would have to do part A on the side. All right. F, I remember, is, so this is a side note. So this equal corresponds to that. F is 2x plus 3. Let me triple check. I'm pretty sure it is. In this example, yep, 2x plus 3. So that is 16x. Since I'm going to actually spell out 24, 8 times 3 is 24, and then we're going to add 13. So we finally end up with 16x plus 37. Yeah. So there. Example 9. Okay, let's say g of x is equal to x squared minus 5x plus 7. And let's keep f of x the way it was before, 2x plus 3. All right, so part A, we're going to do f composed with g. So f goes, the rule of f goes first. We're going to do 2 times whatever the input plus 3. But the input is going to be g itself. See, this gets convoluted, and it's the way it is. It's a normal convolution in mathematics. It's a normal complication that we use all the time. So 2 times the input, but the input is going to be g. 2 times the input, x squared minus 5x plus 7. So that's what f calls for, and we're applying f to g. 2 times the input plus 3. And then the rest is just polynomial computation. So we end up with 2x squared minus 10x. Now here we have 14, but then we're going to add 3 to that. So that's going to give us really 17. G composed with f of x, on the other hand, this is an interesting example, will be, okay, now let's understand what G does. G says take whatever the input is, square it, minus 5 times, bring back the input again, plus 7. So we're going to use the input, whatever the input is, twice, because the formula calls for using it twice. Square the input, multiply the input by 5, subtract those two. After doing that, then add 7. Okay, so that's what we're going to do, except that we're going to apply that to f. F is the input, f of x. So it is important to know how to read this. This is not just saying g of x equals x squared minus 5x plus 7. This is saying whatever the input is, square it. Whatever the input is, again, multiply it by 5. Then subtract those two quantities, and then add 7. So the input is f. So square f, which is 2x plus 3, square. Multiply 5 times 2x plus 3, subtract, and then add 7. Okay. Now it's a matter of computations of polynomials. FOIL this out. So that is going to give us 4x squared plus 12x plus 9. If you don't know where this came from that squaring, pause the video and figure this out. While we keep that there, we're going to distribute the negative 5. So we really have negative 10x minus 15, and then add the 7. All right. There's this parenthesis, we're not really doing anything. I was just keeping the foiling all together. There's nothing to distribute on the parenthesis. So this parenthesis is really irrelevant in this case. So 4x squared, there's nobody to simplify that with, so leave it alone. 12x minus 10x is 2x. And then there's no more x to simplify. So 12 minus 10 x's is 2x. 9 minus 15, that is negative 6, plus 7 is 1. I'm going to think of that again. 9 minus 15, negative 6, plus 7, 1. So we end up with 4x squared plus 2x plus 1. And again, notice that f composed with g, which is 2x squared minus 10x plus 17, is not equal at all to 4x squared plus 2x plus 1. They're not equal at all. They're not even, I mean, they're both quadratic, but that's as far as it goes. The rest, I mean, if you look for more similarities, yeah, they both live in Earth. That's an exaggeration. Sorry to be that exaggerated, but yeah, they're both quadratic and they're both opening up. So you can still look for similarities, but the fact is they're different. They're not the same function. G composed with G brings us an interesting challenge. So this is example C. G composed with G. This is kind of not well written. It's not nicely horizontal. Okay, because we're going to apply this rule of whatever the input is, square it, minus 5 times whatever the input is, plus 7. Let's do it. It's not going to be easy. But let's do it. This is going to take us about double the time of the other examples, or maybe a little longer. Okay, so whatever the input is, square it. But the input is G, which is the entire thing all over again. So we're going to have x squared minus 5x plus 7, and we're going to square that, which is not going to be easy. Then, see, f is not in the picture because there is no f here. It's g composed with g of x. Minus 5 times that very same thing. And again, when I'm doing a function composed with itself, I'm thinking of that vacuum that it's sucking up itself. X squared. I know that's a silly example. Again, this is from, you probably have never seen, if you're watching this video, you probably haven't seen a cartoon from the Pink Panther. And the old cartoons are, I don't know, from the 60s, I'm guessing, maybe 70s, 1970s. If you ask somebody who's in their 50s, they will probably remember. But anyway, okay, so we have to FOIL this out. That is not an easy, and I shouldn't say foiling because foiling applies to binomials, 2 terms, 2 terms. This is 3 terms. So I'm going to do that on the side. So I'm going to pause this computation because we need to multiply x squared minus 5x plus 7 times x squared minus 5x plus 7. And many of you have different ways of multiplying. Some of you will have like a nice, neat table, where you put the polynomial on the top, and then the other polynomial, which is itself on the side, and then you multiply with little boxes. That's a perfectly good way to do it. I'm not saying that's wrong. I just prefer to do this. So 7 times 7 is 49. 7 times -5 is -35x. Keep the 49 with a plus, and then 7x squared. 7x squared. Okay, so minus 35x plus 49. So the 7 multiplied with everybody already. Then the -5x times everybody. So we have -5x times 7, -35x. And I'm already going to line it up so that it adds nicely with the previous term, or with the term that is alike. So this times that is that. Those two together make 25x squared. 25x squared, which I'm going to write under the x squareds. And then this times that is -5x squared. Oh, I didn't give myself enough room. -5x squared, because I think I'm going to need one more over here. All right, well, that is done. X squared times 7 is 7x squared. I want to put that under the x squareds. Oh, there's a plus here. X squared times -5x is negative 5x cubed. -5x cubed. Oh, wait a minute. That shouldn't be an x squared. Where did that come from? That came from multiplying those two. So that should have been x cubed. Okay. And then there's one more term that should be here, but I'm not going to write it on the desk. And that is x squared times x squared. So that is x to the 4. I'm going to put it here plus x to the 4, but it should go over here. So I'm going to shift everything a little bit to the right so it fits nicely. So the 49, that doesn't add with anybody, I'm going to write it here. So I'm just going to shift in this way. That's -70x plus 49. And then 25 and 14 is 39 plus 39x squared minus 10x cubed. So this guy came from here. And then the x to the 4, I'm going to put it here. There we go. So we end up with x to the 4 minus 10x cubed plus 39x squared minus 70x plus 49. Wow. So I didn't want to do all this work. And please double check. So this will be x to the 4 minus 10x cubed, x to the 4 minus 10x cubed plus 39. I was double checking. Yep, 39x squared minus 70x plus 49. That's just foiling this out. Then we're going to take away 5x squared minus 5x squared plus 25x minus 35, and then we still keep the 7. So I'm putting them underneath respective like terms, so it is easier for me to add them together. So we end up with x to the 4 minus 10x cubed. 39 minus 5 is 34 plus 34x squared minus 45x. 49 minus 35, well, 9 minus 5 is 4. So that is 14 plus 7 is 21. So unless I made a mistake, this should be the composition of G with itself. That was a difficult composition of G with itself. Okay, that was example 9ABC. Practice the composition. It is very, very important. Now, the domain with the composition is tricky. Sometimes it isn't. Pretty much all the examples with the composition domain was not a problem, but it can be a big problem. It can be a very, very big problem. Let's do example 10 first. Okay, so example 10 is going to be simple. Let's say f of x is, what is it? X squared. And g of x is going to be 1 over x. Yeah, so this is not difficult. I just want to show how x squared works. So f of x, what I meant to say is f of g of x f of g, or f composed with g of x, will be, well, square whatever g is. So g is 1 over x, and just square it. And then quite often we distribute, so it is simpler to write 1 over x squared. The domain of this g is not 0. X may not be 0. And that domain is preserved here. It is implicit because we cannot divide by 0, but it's a good idea to write it out. Note that g composed with f. Now, what does g tell us to do? Whatever the input is, make a fraction where 1 is the numerator and the denominator is the input. So this is what we're going to do here. Whatever the input is going to be f. Make a fraction with a 1 on top, and in the denominator put f, which is going to be x squared. So notice that in this case, this is one of those cases where f composed with g is the same as g composed with f. They're the same. And the domain is going to be the same. X cannot be 0. Okay, I wanted just to show you what happens when we square. The next example is a tricky example, and that's the one I want to spend a little bit of time with. Say you have example 11, f of x equals x squared. G of x square root of x. This one is a tricky example, and I like to put this kind of example on tests because of the domain, not so much because of what simplifies into, but because of the domain. So f composed with g says, okay, we're going to square whatever g is. So we're going to take the square root of x and square it. And it doesn't take too much to figure, well, we're going to get rid of the root because when we square a square root, we end up with the input itself. But there is one catch here. The input, the original input is of the f is the g, and in turn, the original input of g is all numbers that are non-negative. So there's an implicit domain here where x had to be at least 0 or greater than 0. Well, that domain stays with the combination, with the composition. It does not change. It is inherited in the composition. The domain belongs to G, and that domain carries through. So in this case, x has to be greater than or equal to 0. Or, as an interval notation, we put 0 to infinity. This is the domain of the composition of those two functions. Be very, very aware of that. Yeah. So this is part A. Part B, if we compose the other way. Yeah. And I love to put those examples in tests and quizzes and assessments in general, because I want to check whether students know or remember how the domain works. All right, so this says we're going to take the square root of x squared. Yeah, that is not going to change the domain. The domain is going to be all real numbers, because here the input of G is F. The input of F is all numbers. There's no restriction here. And somebody may say, well, those two cancel. Well, watch out. No, not exactly that way. Because they don't cancel. Oh, because if we had a negative number here, say the input was -3, when we square it, we end up with +9, and this implies the principal root, which is the positive root, so the answer would be 3. So if the input was -3, it would be wrong to put -3 here, because we always want the principal root. So this is incorrect, inaccurate. What we have to have is the absolute value of x. And the domain is all real numbers. Pay attention to those two. Those two are very, very tricky problems. Yeah, I think those two, well, this example is very tricky. One, because this one simplifies to the absolute value, not just the x. And we have all the real numbers as the domain. The tricky part about this composition is that the domain is not all real numbers. It starts with 0, and then we go forward. Yeah. So expect this kind of problem on the test. Yeah. I'm going to twist it a little bit, but not much. The idea is still here. Decomposing functions is even more important when we are talking about composition. Decomposing functions. And remember, we want to decompose in such a way that we don't have, rather than that we have simpler functions. So as an example, 12, h of x equals square root of x plus 2. Let's start with something simple. We're going to be faced with breaking this up into two functions via a composition. And the trick here is that there is going to be a difference in if we decompose one way versus another way. So what we expect as an answer for this problem, okay, so let me write down the problem. So given this, okay, comma, find functions f and g such that f composed with g is equal to h. So that's how we're going to prompt the question. That's how we're going to ask the question. So let's analyze what's going on. We're taking the square root. Okay, pause for a moment. We are taking the square root of, pause. That means that f can do that. F of x can be the square root of, and just put an x, of whatever the input is. And then g is going to take care of the rest, which is the x plus 2. So when we compose back together, we end up with this. So this is the answer that we will be looking for with this kind of problem. If you do this the other way, if you put g of x equals square root of x, and f of x as x plus 2, that's going to be considered wrong. This is good, this is bad in this example. Now, the key, you may be thinking, wait a minute, I'm using the same functions. Yeah, but the order, it matters. We're doing f on g. F calls for adding 2 to whatever g is. So if we were to compose this back together, f composed with g of x, that would be, okay, so whatever the input of f is, add 2. But the input in this case will be g, so square root of x plus 2. So the fact that the 2 is outside of the root makes a gigantic difference in mathematics. Huge, huge, huge difference. Oh, I just missed something. No, that's exactly what we're testing. All those little nuances is precisely what we are after. I mean, if we were so liberal so that this wouldn't make a difference, then I don't know, that defeats the whole point of learning mathematics. Mathematics has to do with paying attention to close details, or paying close attention to details, rather. Um, yeah. So whether the 2 is inside of the root or not, that is very, very relevant. Now, there are trivial solutions to this problem. If somebody said, hey, can I just say f of x equals square root of x plus 2 and g of x equals x, that actually works. But there's a big but happening here. But this is a trivial decomposition. Not allowed. Yeah. When we are decomposing a function, we want to break it up into simpler parts. Square root of x is simpler than square root of x plus 2. X plus 2 by itself is simpler than the square root of x plus 2. So this does the job. This does not break up anything into anything simpler because we still have the square root of x plus 2. Now, it does work, but it's not simpler. I usually have an analogy. It's like if you ask an elementary school child to add, I don't know, 7 plus 8, and the elementary school child says, well, that is equal to 7 plus 8. Did the child lie? No, of course not. That's completely true. It is accurate. But when we say how much is 7 plus 8, we don't mean 7 plus, we don't want the answer back. We don't want the question back. We want a number that results a single number, not two numbers. For that matter, a student could say, well, it's the same thing as 8 plus 7. There are many answers that are accurate, true, or somebody could say, well, that's the same thing as 7 plus 1. There's many ways to break up this. But usually when we ask a student of elementary school to add 7 plus 8, we mean 15, correct? So likewise, doing this is equivalent to just repeating the question back to us. We're not really breaking anything into something simpler. Yet, this is an important example to notice. If we compose with x, we end up with the original one that we compose with. Yeah, and if we reverse those two for f and g, we're still going to end up with something that works, but is not allowed. And then there is the overcomplicating answer. Somebody could say, well, can I make f of x equal to, now I got to think about this because it has to be right. Let's say g of x equals the square root of x plus 2, and then we're going to add 10 to it. So when we put it here, x minus 10. So when we compose, we're going to do f of g So this would be the input, which adds 10 to the root, and then here we subtract, so those two 10s cancel each other. This works. It does the job, works as far as obtaining h of x equaling f composed with g, but there's a huge but. This decomposition is unnecessarily complicated and doesn't simplify the parts, and we do not achieve the simplified parts. So not allowed. Yeah. So this is just a trick. It's like a scam kind of way of answering a question. I don't know if that's a good way to describe, but it's not really doing anything. It's just adding more to it. It's like going over more salespeople kind of thing. Now, nothing wrong with salespeople. What I mean, additional sales. Like, so instead of going through one salesperson, you go through a chain of salespeople, and I don't know. That maybe that's a bad analogy, but this is more. Why the 10 has nothing to do with the original problem. Adding the 10 into it is just we don't achieve anything. We don't get anything that is simpler. So the answer that we want in this case is something like this: simple x square root, simple x plus 2 together, they combine into this. Make sure that it is in the right order, and then we go from there. So decomposing is very, very important. It has to be done well. We cannot allow trivial solutions, and we cannot allow things that are more complicated either. Okay. Sometimes we ask the decomposition with either a graph or a table. So I want to show you a quick example with a table, but it is just as good with a graph. So example 13. Okay, so this is a table example. So let's say I give you a table x, f of x, g of x, and let's keep things simple. We're just going to have 4 inputs, 0, 1, 2, 3. That's it. And the outputs, I'm going to put the outputs at random here. So let's put the 0 here, and a 1 here, and a 2, and a 3, and a 0, and a 1, and a 2, and a 3. There we go. Okay, so given this table, so what is the function? What is the formula? We don't know. There's no formula. It's just a table. So no equation. That's different about what is different about this. So I can ask you a whole bunch of questions. So let's start with f composed with g of 2. Whoa. So that means find g of 2. G of 2 is 2. Oh, that was a coincidence. Okay, so g of 2 is 2. Well, let me write it differently. So this is f of g of 2. It's a little confusing that g of 2 is 2 itself. So that is really f of 2, and f of 2 is 0. Okay, let's do another one. B. F composed with G of 3. Okay, that would be F of G of 3. Okay, so first we look for G of 3. G of, no, not G of 3. G of 3 is 1. So that is really F of 1, and then F of 1 is 3. C. How about G composed with F of 2? So now I'm reversing the first subexample. G of F of 2. Now F of 2 is 0. So we're really looking for G of 0. G of 0 is 3. So I'm giving two outputs for one input. Instead of giving two tables, I'm giving only one table. Yeah. Be aware that I may give you one table or I may give you two tables. So another way to write the same information, so same problem, but I'm going to write it in two tables this time so that you know the difference. So x 0, 1, 2, 3, f of x will be, I'm copying the same thing, 1, 3, 0, 2. 1, 3, 0, 2, x 0, 1, 2, 3, g would be 3, 0, 2, 1. 3, 0, 2, 1. So that is another way to provide the same information with one table for f, one table for g. Here's g of x, g of x. Okay, so let's say we want to find the g composed with f of 3. Okay, let's use this table now instead, those two tables. So this calls for g of f of 3, f of 3, 3f is 2, g of 2, and g of 2 is 2. But don't be confused. Those two tables are the same as this table. What I'm doing is instead of writing 0, 1, 2, 3, 0, 1, 2, 3 twice, I'm doing 0, 1, 2, 3 once, and I'm putting the f and the g in two rows. Do not get confused. Sometimes I do this, sometimes I do that. And now that I'm thinking about it, I could probably do one problem on a test with this information, one problem on a different problem with this information to make sure that, or to see if one is better than the other for students. E, oh, don't forget we can do F composed with F. Let's say 1. So F of 1 is 3. Oh, that's F of 1. F of 1 is 3. So this part is 3, but then we still have to do F of that. F of 3 is 2. Yep. And sometimes instead of giving you a table or two tables, we give you a graph. So I'm going to sketch the graph real quick. So we got 0, 1, 2, 3, 0, 1, 2, 3. So if we graph F, 0 goes with 1. So 0, 1. 1 goes with 3. 2 goes to 0. So this is 2. 1, 2, 3. 1, 2, 3. So 0 goes with 1. 1 goes with 3. 2 goes with 0. 3 goes with 2. And let's pretend we had a broken line. So the way the graph would look is this way. So that would be F. F, while G goes 0, 3, so it starts up here, 1, 0, dives down here, 2, 2, 2, 2, 3, 1. So the graph of G would be this. Okay. So make sure you know how to read the graph. So how can we give you the information? At least in 3 different ways. Well, actually more, because we can have an equation or we can have no equation. If we have no equation, we're going to give you a table with the consolidated information of F and G, or 2 tables, one for F and one for G, or a graph with F and G. Okay, so let's do more of this, and let's actually ask more questions. This is still example 13, and different kind of questions. So where did we stop? What letter? E. So we did A, B, C, D, E. Let's do F. How about F plus G of 3? Whoa. So watch out. This is not a composition. This is an addition of outputs. So F of 3, and pretend we don't even have the table, just the graph. F of 3 is 2, and G of 3 is 1. So 1 or 2 plus 1, 2 plus 1 is 3. Actually, let me break this up. F plus G of 3 is the same thing by definition as F of 3 plus G of 3. And so F of 3 is 2, G of, there's the F of 3. G of 3 is 1, so that's how we get 2 plus 1 equals 3. FG. How about F times G, not to be confused with the composition of 1. Okay, let's do this. So this means F of 1 times G of 1. So on the table, on the graph rather, F of 1 I can see is 3. So F of 1 is 3. G of 1, G of 1 is 0. Oh, G of 1 is 0. So the answer is 3 times 0, 0. Okay. G, H. One more. So let's do F composed with G composed with F of 0. Whoa. Okay. Now, even though the composition is associative, we really want to go this way. F of G, whoops, F of this is really annoying when it doesn't work too good. Anyway, F of G of F of 0. So close this parenthesis, close one, close that one. Okay. So we go from the inside out. What is F of 0? F of 0 is 1. So again, sorry, I wasn't showing you. F of 0 is 1. By the way, we're assuming, pretend we don't have the table, that we just have the graph. So we have to draw the information from the graph. What I have seen students do sometimes is they don't look at the problems. They come up with the tables, because from the graph, you can come up with the tables. And then they look at they use the tables. That's fine. I don't have a problem with that. If you want to use the tables, from the graph. As long as you yourself come up with a table, that's perfectly fine with me. So a student would say, okay, that is 1, 3, 0, 2. They just go and actually look at it. 1, 3, 0, 2. So they put them down 1, 3, 0, 2. And then they go 3, 0, 2, 1, 3, 0, 2, 1. So they actually write it out. And then they do this using the table. Either way is fine. The problem is that if we have several of those questions and you use the, let's say we make a mistake, because all of us can make mistakes anytime. If we make a mistake here and then we answer 3 questions with the table and the table had a mistake in it, then that mistake can cause us to have all of those problems wrong. So watch out, because we don't want to make mistakes that will carry on several problems if we can avoid it. Anyway, so f of 0 is, there's f, 0 is 1. So we're doing, so we just figured out f of 0 is 1. So we are still doing f of g of 1. F of g of 1. Now we're going to do g of 1. G of 1 is 0. So g of 1 is 0. So we're really doing f of 0. F of 0 is 1. Boy. So that's the way we go about it. We go here, figure out f of 0, whatever the answer is, g of that answer, whatever g of that answer is, we do f of that answer. So these are 3 steps we have to go through. Composition of functions can be a lot of fun. It is a lot of fun. So we're going to stop this video here.